Welcome back, everybody. This is really just stacked graphs right here, but I'm going to use this video to point out our equations that describe either displacement or position, I should say, position, velocity, or acceleration as a function of time. And these are equations that we've been using, but you're going to use these equations specifically to describe the shape of a graph, one of these graphs right here. Again, this part right here is towards the back of your notes. We didn't hit these very hard because they're not really stacked graphs because they're not stacked vertically on top of each other. I will put an answer key for all these online for you to check out. But for right now, just go to this page in your notes. Positive acceleration starting from rest at the origin. And I want to write down our three equations that describe the motion of this object right here. All right. Now, first of all, let's go ahead and write what each of these looks like. All right. Positive acceleration starting from rest at the origin. All right. Well, positive acceleration means that our acceleration is going to look like this. It's just some positive value right there. And in our class, we're not going to be dealing with changing accelerations, and so it's just going to be constant, straight across like that. All right. Some constant value in our acceleration versus time. Velocity versus time is going to look like this. Starting from rest. Okay, so it starts with zero velocity. But what happens to velocity? It increases positively because we have a positive acceleration. So over time, it's going to increase at a constant rate. That is, the velocity is going to increase at a constant rate because we have a constant acceleration. Lastly, we've got position versus time, and I'm sort of doing these backwards, as you can see. Starting from rest at the origin. All right, so once again, here is our beginning position, the origin, and it's starting from rest. All right, so we've got an initial slope of 0, but over time, that slope is going to become steeper and steeper and steeper and steeper and result in a curve for this position versus time graph. Okay, so you should have something like this probably in one of your stacked graphs already, except not horizontal, but they're actually vertical. They're actually stacked vertically. All right, so let's just take this one, and let's write some equations for each one. Remember, we've got a positive acceleration. All right, initial velocity is at rest, so that's telling us about our initial velocity, and at the origin tells us about the initial position right there. I am going to go forward now. So really, if you were to write an equation for this first one, which is position versus time, you would have an equation. You'd probably be asked something like this. What is the position, and I messed it up already, the position as a function of time? All right, what is that? All right, well, we have an equation that actually describes that right there, but we need to kind of tinker with this a little bit and change it around to be in terms of what make more sense to us. Position as a function of time. Well, what this really means is that what is the position after a certain point in a certain amount of time has elapsed. All right, if we're talking about this amount of time right here, that would be that position. This amount of time, that position. This amount of time would be that position, and so forth. So just like in math class, you learn about f of x, the function of x. Well, this really means what is the y value right here as a function of time. Or in, like I said just a minute ago, in more common terms, we can really think of this as being our final position. Our final position after time has elapsed, right? Because final usually means after time has elapsed. What is our final position? What equation do we have to describe that? Well, we've got an equation that looks like this. Our final position is a function of our initial position plus initial velocity times time plus 1/2 acceleration times time squared. Now, where did this come from? Well, what we usually do is we usually have this x initial added over to, or so subtracted over to that side, which means the left-hand side is delta x. But if we break them into the two parts, x final and x initial, we can put x initial over on this side right here, and we can have this all be in terms of x final. X final is really what x as a function of time really means. Okay, so this is our equation that describes the position of an object after any amount of time. If there's an acceleration Or even if there's not, what if there was no acceleration right here? That part would become 0. If there's an initial velocity, what if there is no initial velocity or acceleration? Well, that becomes 0. So this tells us what the final position of an object is after any amount of time has elapsed. Okay? All right, next. What is our velocity as a function of time? And I keep writing F. I really want to write T. Okay? What is our velocity as a function of time? Well, that's described by an equation as well. Remember, velocity as a function of time really just means final velocity after some time's elapsed. So we've got an equation for final velocity. Final velocity is a function of the initial velocity plus the acceleration times time. All right, now in this case, the initial velocity we know to be 0. Right? We know an initial velocity right there. And so what the final velocity is depends on this acceleration. That is the slope of this line right here. That'll tell you what the final velocity is after some amount of time has elapsed. All right, so that amount of time will return us that final velocity right there. So if you were given values for initial velocity and acceleration, you would be able to write this equation out right here with the actual values and have final velocity as a function of time be written in terms of time. This last one's actually going to be pretty easy. Acceleration as a function of time. How is this acceleration changing with time? It isn't. It is constant, and that's really what's going to be true of this class. We're going to be dealing with constant accelerations. Any change in acceleration is something that's called jerk, and we're not going to worry about that. All of our accelerations are going to be constant accelerations. And so your acceleration at any point in time is simply going to be whatever the original acceleration was. A. Well, that's easy, okay? So that would be your equation for A, acceleration as a function of time. That would be your equation for velocity as a function of time. And this right here would be your equation for position as a function of time, but you would use these down at the bottom and plug in the values that you have. Okay? So that's it for our equations that describe a kinematic graph. Get used to looking at those and using them, because you may be asked to interpret a graph using those equations in the future. All right, thanks for following along. See you on the next one.